Welcome to this presentation on queuing systems and message brookers. Today we will explore the fundamentals of message brookers like RabbitMQ and Kafka, their importance in system design, and how they help create scalable and resilient applications. In this session, we will cover several important topics, starting with an introduction to message brookers. Then we will dive into the key concepts behind RabbitMQ and Kafka, two popular message brookers. We will also discuss how these systems fit into high-level design along with design patterns and best practices. Finally, we will conclude with a summary of the key takeaways. Message brokers are intermediaries that enable communication between decoupled services using asynchronous messaging. This allows systems to be more efficient, reliable, and scalable. Key features of message brokers include enabling asynchronous communication, decoupling services, ensuring reliability and fault tolerance, and providing scalability for handling large volumes of data. Let's now look at RabbitMQ, which is a traditional message broker that follows the AMQP protocol. RabbitMQ uses key concepts such as queues to store messages, producers to send messages to queues, and consumers to process those messages. Exchanges route messages to queues and binding link exchanges to those queues. RabbitMQ is widely used in scenarios like task queries, workload distribution, and request replay patterns. Next, we have Apache Kafka, a distributed messaging system that excels at high throughput and real-time event streaming. Kafka's core components include producers who publish messages to topics, consumers who subscribe and process messages, and partitions that divide topics to enhance scalability. Kafka is great for event streaming, log aggregation, and building data pipelines. Queuing systems play a crucial role in high-level design by facilitating asynchronous communication between services. They help with load balancing and scalability by distributing workloads across multiple consumers. Additionally, they ensure fault tolerance, ensuring that messages are not lost, and allow for rate limiting and throttling to prevent system overloads. There are several design patterns used in message brokers, including the publish subscribe pattern, where messages are broadcast to multiple consumers, the work queue pattern, which distributes work across multiple consumers, and the competing consumers pattern, where multiple consumers compete to process messages from the queue. These patterns are essential for building scalable, resilient systems. To implement message brokers successfully, several best practices should be followed. Ensure that messages are idempotent, meaning they can be processed multiple times without side effects. Use message acknowledgement to confirm that messages are processed successfully. Implement dead letter queues for failed message processing. Monitor the performance of our brokers and handle backpressure effectively to manage high message inflows. To summarize, queuing systems and message brokers are essential for building scalable, resilient, and decoupled systems. RabbitMQ is ideal for traditional message queuing, while Kafka excels in real-time event streaming and high-throughput applications. By following best practices like idempotency, acknowledgement, and monitoring, we can ensure that message systems remain reliable and effective. Thank you for your attention. That concludes our presentation on queuing systems and message brokers. I now welcome any questions or discussions you may have.